Uh, First thing we need to do is define a density curve. And that is a distribution. Okay, and let's pause on that word because I feel like that word, we hear it so many times in stats, but like it's kind of vague. It means a data set of numbers. So, and sometimes a data set of numbers is represented in a histogram or a box plot or a dot plot. In our case here, we're going to use a mathematical model for a set of numbers. But anyway, just when you see that word distribution, think set of numbers. And it models a quantitative variable, which means a measurement, some type of whatever it makes sense to take the average of. So specifically numbers. And what I want you to think about, I want you to pretend that you're in chapter one, not chapter two. And I want you to look at these curves and imagine that there's a rough histogram living underneath there. And that you kind of glaze your eyes over a little bit and you draw like a curve over it to represent the shape of that histogram. Does that make sense? Okay, so pretend there's a histogram living behind this, and then somebody took and like glazed their eyes and made a general shape of a curve over top. So this one, the tail is going to the left, so it's left skewed. Just pretend there's a left skewed histogram living there. These are mathematical models, just like line of best fit, these are curve of best fit. Okay, there's two things that you need to know about this, and it's going to sound like calculus, but it's not. So they are always above the x-axis. Fascinating. And this is the part. The area under the curve always equals 1. Again, it's going to sound like calculus. It's not, I promise. We're not going to be calculating areas under the curve that are not this particular shape. But when we say equals 1, it means that there's percentages. So if you would shade in the whole thing, you would shade in 100%, basically is what I'm saying. Okay, now we're going to go back to some chapter 1 stuff. And I want you guys to turn your notebook sideways. And we're going to write what these statistics would be. So I want to remind you that the mode is the most. The mode should be the highest point in your curve and also the highest point in your histogram. It's the thing that occurs the most times. In this case, because of the skew, the median would be closest to the mode. And then the mean would be pulled into the tail because it is not resistant to outliers. So the mean is affected by outliers, means it will be pulled into the tail. You guys knew that already, right? Okay. All right, so now come down here to this guy. This guy's called bimodal. So these are both modes. Sometimes graphs have two modes. Sometimes graphs have two modes that aren't the same number. And the mean and the median will both be in the center because this particular one is symmetric-ish. I mean, it's still Mrs. Talbot drew it, so it's not perfect, but.
Okay, so how should we label the last guy then? What would the first line be? Mode, because it's the highest, yep. Then what would be closest to the mode? Median, because it is resistant to outliers. And then the mean would be pulled into the tail because it is not resistant to outliers. Any questions about that stuff? Okay. Last thing I want to do here is put the shapes underneath. Okay, next section, uniform density curves. So let's think about a uniform shape. My favorite way to describe it is like after Mr. Talbot cuts the grass. You know, it's pretty even along the top, but like some little pieces of grass are a little higher, some pieces of grass are a little lower. Or like somebody that gets a buzz cut haircut, you know, it's almost perfect. And when you model that, so you gloss your eyes over, it's basically a rectangle. So uniform density curve is just a rectangle, which is great. That makes the math super easy. Okay, it says draw the uniform density function to represent the situation. We did, it's done, except we need to label what the height would be. So over here, you're going to say area equals base times height. This is going to be the formula you're going to use for all uniform density functions. Base times height, you know, crazy complicated formula there. And we know that the area under the curve has to be 1 because that's a density curve. So the area has to be 1. And the base is how long? 40. And you can tell it says 40 years in the problem times the height. One divided by 40 is 0.025. So I labeled on the height. Okay. B, about what percent chance is there of having an earthquake between year 16 and year 32? Okay, so this is where we're going to start arts and craftsing. What I want you to do is draw a line as best you can at 16. And draw a line as best you can at 32. And then pick any color that you like or not. It doesn't have to be colored. I just think it's fun. If your hand already hurts from last night's homework, you might not want to. Okay. So the question is saying about what percent chance is there of having an earthquake between year 16 and year 32? in geometry language, it's saying what is the area of the rectangle that you shaded. Okay, so we're going to say area equals base times height. Area equals, okay, now the base, how long is the base? Mental math in the morning. Okay, I don't really know. I mean, I do know, but for the case of notes, I'm going to put 32 minus 16. I'm just going to say far minus near, basically, because I'm going to type this in the calculator. And then the height is 0.025. Are you guys okay if I already did this arithmetic ahead of time just to save us time? Okay. So this comes out to be 0.4, which is a 40% chance. Okay, correct me if I'm wrong. This is where you left off with setting up the notebook, correct? Okay. Thank you. Sorry.
No, okay. Mm.
Okay, guys, let's finish this up. This is super easy. Estimate the 60th percentile of years before an earthquake. So I want you guys to, if you have room here, you can put it down here if you want. If you have room right here, I want you to kind of read these two words, 60th percentile, and I want you to interpret that in your brain as 60%. So 60th percentile, 60%. And what this is asking you is if I shaded in 60% of this rectangle from 0, what year would it be on the x-axis? So this is asking us to go backwards from what we did a second ago. So area equals base times height. And this time you have the area because you're going to take that 60% and convert it to a decimal of 0.6. So 0.6 equals base times 0.025. Divide by 0.025. And 24 equals the base. So that means the 60th percentile of years before an earthquake is about 24 years, using those units from the x-axis. Okay, now this last part, if you took calculus, you're gonna not want to argue with me. If you did not take calculus, you might want to argue with me. We'll see. There's always an argument every year about D. It's first period, so there might not be. What we want to do is go back to our rectangle, and I want you to draw a line as best as you can at exactly 1 year. So this question is asking, what percent chance is there of having an earthquake in exactly 1 year according to a uniform density function? And these percents are areas. How much area is there in a line? Yeah, okay, so what's the base? Well, what's the base? 0. This is that's where the argument's going to come from. The probability is 0 according to this mathematical model because these probabilities are areas and lines don't have any area. See your faces every year. Okay, so if it says about what percent chance is there of having an earthquake, exactly some number, the answer is 0. Okay, and there's so many of you thinking, but Mrs. Talbot, it could happen. Okay, and let me tell you that this is going to happen all year. We're going to deal in theoretical probability. This is theoretically, mathematically, the probability is 0. Just like when I tell you to toss a coin, you should, get heads and tails and heads and tails, but that's theoretical. You could get heads for the rest of your life. You don't know. So there's a difference between actual events and theoretical probability with modeling. What's wrong? So all you need to know here is if it gives you just a number and not like a between two numbers, it's 0, mathematically speaking. Okay, if you want to think about it, what's the probability of there being an earthquake 1 year from now, exactly at this second, right now, or right now, or now, or now, or now, 0 each time, because it's such a tiny little bit of time. Just try to wrap your brain around it. Yeah, let's not have an earthquake though. Okay, so next section, so that part's done. We have 2 sections today, 2.2a and 2.2b.
2.2a is done. 2.2b is about the normal curve, and it's probably the most important thing that we learn. Because I don't know if you guys notice in stats, it's like the thing everyone sees, the bell curve. And you're gonna use it in AP Psych, and it's used in all areas of research. And it's just the most common. Like if you think of stats, you think of the bell curve. Today, the math is very, very easy. I promise. First thing you need to know is that it's symmetric and bell-shaped. Symmetric and bell-shaped. Which means for us, the mean and the median are equal. And they're both going to be on that middle line. You can see my big curve back there. The mean, the median, and the mode will all be the same thing at 0 on that bell curve back there. And the other thing that you need to know is going to be fun for you. It's defined by its mean, which in this case is lowercase mu. And its standard deviation, which is lowercase sigma. And it goes out about 3 standard deviations on each side, every single time. That's why the chickens, when they said the 3 standard deviations above the norm, was so exciting. If somebody told you that, you should be really like grateful that they said that, because that means that you're all the way at the top. Okay, now can you guys just pause, rest your hand for a second? I need to go back, and I'm going to put this on video, which is great because you're going to need it later. I promise. I'm going to go back to our lesson from Monday real quick. And I want to talk about this again. Okay, so you're all looking up here. You're all focused because this is one of those things that's confusing, so I need to go over it. Okay, remember how I said that you're looking at a curve and there's a histogram living underneath it that comes from real data. So you got a data set of numbers. Look at me go. I'm like, Diana White. You guys know who she is? No, you don't. You're too young. She's the Wheel of Fortune lady. Anyway, okay. So you got a data set of numbers, and you went home with your calculator, and you put it in a one variable set, and you made a histogram, right? Okay. So you got your histogram. In that case, you would do this x minus x bar over s of x. X bar and s of x both coming from your calculator's one variable sets. Are you with me? Okay, then you like put that paper down on one of those like light tables. You know what I'm talking about? Like a tracing table. And you put another piece of paper over top, and you went like this with your eye, and you made a curve over top of it as a mathematical model of your data. So it's not like anymore. It's like, okay. That mathematical model is theoretical. So that's when you use mean and standard deviation, fancy, like for your model. So this is modeling real actual numbers. Model calculate. Okay, that's why the numbers are different. But they're still the same thing. That's still the mean. That's still the standard deviation. It's just the theoretical mean. Because when you read a research study, a lot of times they don't give you all the numbers. They just give you an average. So then you have to go, okay, well, I don't have all the data, so I got to go with an approximate shape. I can't make the full histogram. Okay. That was fun and embarrassing for me. My hat is too big. My noggin is too small. That might explain my brain problems. I need my brain to grow, and my hat would fit. I don't know. I think I have short-term memory loss. Oh, did you think I wasn't going to work that joke in at some point? Okay, anyway. Okay, empirical rule. So if you Google this, this is what you're going to find. 68% falls in one standard deviation. 95% falls in two standard deviations. 99.7% falls in three standard deviations. Okay, and before I give you arts and crafts time to set up the rest of this, I want to come back to my giant normal curve magnet. And I want to point out that's what these intervals down here are saying. So let's just say you have all of those numbers that you got, right? You've got a data set of numbers. If it's normally distributed, 68% of them will fall in this region here. This is a very common region. These are very usual numbers. And then 95.4% will fall within two standard deviations, which is more unusual numbers. And then your really high numbers will fall in here. Your really low numbers will fall in there. Does that make sense? So those are very unusual numbers in your data. If it follows this. Okay, notice my numbers on this magnet are more precise than the numbers in the empirical rule. That's because if you're doing like psych, they don't really care enough to be precise to go down to the decimal. They're just like 68%. Like science, they're just like, round it to 68%. And it's good enough for a lot of things. Okay, also, when you're drawing this guy, which I like to refer to as Dart helmet, does anyone at all in the room get that reference? Dart helmet. Spaceballs, there's this movie called Spaceballs, and the guy, he's like Darth Vader, he's got this huge helmet, and whenever I draw this, it just reminds me of that. I don't know, because I'm a weirdo, but what I do is I draw x-axis, and I go up 1, 2, 3, 4, 5, 6 boxes here, and then I go over 2 and up 3, and then over 2 and up 1, and then I try my best to connect this. However, if you look in your packet, I printed you a bunch of them, so you don't have to draw them every time. You can just use the printed ones, but this one we're going to put in our notes. Right. Mm-hmm. I don't know. Okay, so this is what I need you to do. I need you to cut and paste that in. And then I need you to kind of abandon ship on your notebook and find your packet.
So draw this. Abandon ship on your notebook when you have this situated and find the giant normal curve in your packet. Okay, everybody. So we're going to make a normal curve in our packet. And we're going to color it and things. What I suggest that you do is we're going to color the middle two sections the same. So I'm going to take these and label them with the empirical rule, 34%, 34%. Because it says that middle part is 68%. There's one standard deviation away. And then it said two standard deviations away is 95%. So would it make sense to you if I did 95 minus 68 divided by 2? Okay. Is it okay with you if I already did that in my head? Okay. So these two sections will be 13.5%. And then it goes out 99.7 to here. So these guys are 2.35%. And then out here, where they don't even acknowledge anything, is 0.15% of your data, which is going to be like an extremely unusual number. Okay. The next thing we're going to do is label on the z-scores. So right over here, z-scores. -3, -2, -1, 0, 1, 2, 3. A reminder, the z-score definition is how many standard deviations away from the mean. So how many of these sections away from the mean. And the last thing we're going to do, if you don't have a straight edge, you might want to grab one, is we're going to label in the approximate percentiles, and then we're going to color it. Let's do the simple and obvious. What percentile would this be right here? Okay, let me give you a hint. It's halfway up the curve. 50th. Okay, there's a couple of ways you can tell. First of all, it's halfway, but second of all, if you add up all of these decimals, you would get 50%. Okay, now that being said, if this is 50, what's this? 84, right? Does that make sense? It's 84? Okay. Okay, now I have to add decimals in my mind. 97.5. We don't really usually talk about percentiles and decimals, but we're getting the idea. 99.85th percentile. This is really just more for your visual reference here. Okay, so what's 50 minus 34? 16? Minus 13. Oh, no, I'm just, that's 2.5. Okay. Okay, I'm gonna give you all the way till 9:30 to relax and chat and color this in. Definitely speak to each other. Doesn't have to be stats related, just some fun topic if you can think of something. I have a fun topic. Do you guys know those giant beetles that look like cockroaches? They're coming out right now, like bad. So 3 nights ago, Mr. Talbot like jumped out of the bed in the middle of the night and like threw the light on, and there was one of those on his pillow.
That's like, okay, you want to know what
Snakes, minus snakes.
Snakes?
I can't do snakes.
My sister hates snakes. That's fair. Snakes are scary.
Yeah, do I?
I hate
In Missouri, and we were out on a pool house, and the pool house wasn't doing that. They had to cut a pipe that took the drain, like the draining system from the top to the lake, so they had to cut it, and our contractors never covered the hole. And we had friends staying in the pool house, in the pull-out couch, and then one morning he goes into a suitcase to find something.
No.
And
No,
there's
that's
a water snake in his suitcase.
In his
So he closes the suitcase and runs outside and takes it and like throws all the stuff out and then finds the water snake and kills it. But basically the water snake crawls up the pipe into his
It was
suitcase.
a 3D effect.
Do you think that because our house is being remodeled and there's like holes in the floor where the toilet used to be and stuff, do you think that's how they're
You should put a paint can on top of that.
we have a board on top of it, but like so apparently what happened was Mr. Talbot stayed up all night researching like bug sprays, and he found some bug spray, and then that got delivered from Amazon yesterday, and then he mixed up a bunch of it. It was like spraying it all over last night.
Yeah, we have pest control come every like 2 weeks.
Every 2 weeks?
Every 2 weeks.
That's
We
so
spray for
odd.
like ants, spiders.
Well, you still live there, so clearly they didn't just attack it.
There were ants in here
No, 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 my
yesterday.
house right now. The one I was talking about was my lake, with our lake house in Missouri.
You have an ant problem? I lived there like 3 7
did, but not like, not like.
What other color is Hank? I was trying to make this Hank themed. Blue?
Also, blue is like blue.
Hold on. Oh, yeah, yeah.
Look, you're more afraid of ants than you are of spiders. But spiders can like actually, I mean, some ants. There's some ants in like Australia that like you'd be surprised to find yourself in Australia.
All right, 9:30. Cease your coloring, please, and label, guys. Cease your coloring and label your normal curve. We are so close to being done. We have to label our curve, and then we have an A and a B example, and then we're done. Cameron, was it that bad? What? The note, you said you didn't want to do it. Oh, period. Okay, that's good. That's all I wanted to do. I will just tell you, there's a candy involved in chapter 3. So, if that's to look forward to. Oh, yeah. When we get to chapter 3, there will be starburst. Yes, yes. So, chapter 3 is about scatter plots, and I have this data collection thing where you measure how big your hand is from your pinky to the end of your thumb, and then you see how many starbursts you can pick up, and that's a point on a scatter plot, and we're all going to do one, and it's going to be great. Yeah, I think so. I'm a little bit nervous about how many starbursts that's going to require me to purchase.
Oh,
Yeah, I have 2 periods. We'll see. I mean, you definitely will be able to eat some of them, but if you have like, I don't know, I have to see if I can find like a bulk starburst purchase.
I bet you can order them off like Costco or Amazon.
Yeah, I'm gonna try.
Yeah.
My goal is to have you take the ones that you touch, because otherwise it'd be kind of gross. At least they have little wrappers.
Now they're selling Halloween candy.
It's true. Okay, guys, let's finish this up. Example, sketch the normal curve representing this scenario. A bottling plant fills soda bottles with a mean amount of 502 and a standard deviation of 1.8. Notice this problem is a real life example problem, so it's not going to have a mean of 0 and a standard deviation of 1 like we drew in our picture. So what we need to do is take the 502 and put it in the center. So that's where the 0 would be from our picture. And then we need to add and subtract 1.8. So 502 plus 1.8 plus 1.8 plus 1.8 Does that make sense so far?
Yeah.
So the middle, and then each jump is a standard deviation. Okay, so now I'm gonna go to the other side. $502 minus 1.8 minus 1.8 minus 1.8. Okay, and then just because we're sophisticated individuals, we're going to label this okay, and then I'm gonna get that colored pencil back out. What proportion of bottles are filled with less than 500.2? Okay, so less than 500.2 would be all of this area here. Does that make sense to you guys? Less than 500.2? Yes. Okay, so we're just gonna add up those three percentages for our work. So 0.15% plus 2.35% plus 13.5%. And then we did this on our in the packet. So we marked this as what percentile? It was 16. And we have one more question and then we're done. And I have a joke for you. Don't let me forget. Can anyone venture how to proceed with this problem? What do I do between 498.4 and 503.8? It's not rocket science. You guys are like, is there something I'm missing? No, really, you just add the percent. It's you're looking at each other like, does she want something else? 13.5% plus 34% plus 34% is 81.5%. Okay, now we'll just note for where this is going. So not tomorrow because you don't have me tomorrow, but Friday, I'm going to teach you how to find those percents when the question is asking for something that doesn't fall exactly on one of those lines. So like if I said between 500 and 504, those are not exactly on those lines. So the calculator actually has a function where it will calculate that for you. It'll
do the, put the proportion in for you, and it's gonna be great, and it's all calculated, and it's gonna be wonderful.
If you've heard of it before, it's called normal CDF. Okay, joke time. No, that's an email, can't show that. Let's see if I can fix it. Okay, quick check. Did we define and describe density curves? Did we solve problems using uniform density curves? Did we define, sketch, and describe the normal density curve? And solve problems using the empirical rule? We did all that stuff. Look at us go. Okay, homework is 41 to 51 odd, and there is my joke. Oh. By the way, they make shirts with that on Amazon. Just say.